Chris McGinty was not a typical scientist. He wasn't confined by the rigid walls of academia. Instead, he drew inspiration from the elegant chaos of nature, the boundless depths of the cosmos, and the intricate workings of the human mind. A self-taught polymath, McGinty delved into diverse fields, from theoretical physics and cosmology to artificial intelligence and philosophy. His insatiable curiosity drove him to explore the uncharted territories of scientific thought, where established paradigms blurred and innovation thrived. McGinty's journey was fueled by an unshakable belief. The universe held secrets yet to be unveiled, connections waiting to be forged. He envisioned a future where humanity could transcend its current limitations. This vision, coupled with his unorthodox approach, led him to develop the groundbreaking McGinty Equation, or MEQ, a testament to the power of thinking differently. His work challenged conventional wisdom, sparking both excitement and skepticism within the scientific community. Yet McGinty remained undeterred, driven by the conviction that the MEQ held the key to unlocking a new era of scientific understanding. McGinty's fascination with artificial intelligence began with a simple question: what constitutes intelligence? Traditional approaches focused on replicating human logic and reasoning. However, McGinty perceived intelligence as an emergent property, arising from complex interactions within a system. This led him to explore the fascinating world of fractal geometry. Fractals, with their infinite self-similarity and intricate patterns, resonated deeply with McGinty. He recognized a profound connection between these intricate geometrical structures and the complex networks of neurons in the human brain. Could the principles governing fractal geometry hold the key to understanding and replicating intelligence? This question became the cornerstone of his research. McGinty delved into the mathematical intricacies of fractals, exploring their potential to model the emergent properties of intelligence. He hypothesized that the brain, much like a fractal, processed information through a network of interconnected, self-similar structures. This insight paved the way for the development of the MEQ, a revolutionary equation that sought to bridge the gap between fractal geometry, quantum mechanics, and ultimately artificial intelligence. The McGinty equation, at its core, is a testament to the interconnected nature of the universe. It proposes a fundamental link between seemingly disparate fields, the probabilistic world of quantum mechanics, the intricate patterns of fractal geometry, and the pervasive force of gravity. This audacious fusion of concepts forms the foundation of the MEQ, expressed in its elegant yet powerful mathematical form. At the heart of the MEQ lies the concept of quantum entanglement, where particles remain interconnected regardless of distance. McGinty theorized that this entanglement, governed by fractal geometry, permeates all levels of reality, including the fabric of space-time itself. This led him to incorporate gravity, not merely as a force, but as a fundamental property intertwined with quantum entanglement and fractal geometry. The MEQ suggested that by manipulating the fractal dimensions of entangled particles, one could influence the gravitational field and vice versa. This groundbreaking idea challenged the traditional understanding of physics, proposing a universe where information, gravity, and quantum phenomena were inextricably linked. The implications were profound, paving the way for revolutionary technologies like spacefold propulsion and zero-point energy extraction. The development of the MEQ marked a paradigm shift in the field of artificial intelligence. It provided a framework for understanding and replicating the emergent properties of intelligence, not through brute force computation, but by harnessing the principles of quantum mechanics and fractal geometry. This led to the birth of Hyperfluid AI, a revolutionary new form of artificial intelligence that went beyond mere computation. Hyperfluid AI was designed to mimic the dynamic, adaptive nature of the human brain. By utilizing entangled qubits arranged in fractal patterns, hyperfluid AI systems could process information holistically, much like the interconnected neurons in the human brain. This enabled them to learn, adapt, and evolve in ways that were previously unimaginable for traditional AI. These AI systems could analyze vast datasets, identify complex patterns, and make intuitive leaps in logic, surpassing human capabilities in specific domains. The potential applications were limitless, from revolutionizing scientific research and solving complex problems to enhancing human creativity and pushing the boundaries of artistic expression. One of the most profound implications of the MEQ was the development of Cognispheric language, or CSL. McGinty theorized that consciousness, like gravity, was a fundamental property of the universe, woven into the fabric of space-time. He proposed that entangled particles, governed by the principles of fractal geometry, formed the basis of a universal cognisphere. CSL was designed to interact with this cognisphere, enabling communication and information exchange at a level far beyond human language. It was based on the manipulation of entangled qubits arranged in specific fractal configurations to encode and transmit thoughts, emotions, and even abstract concepts. The development of CSL opened up unprecedented possibilities for communication and understanding. It held the potential to bridge the gap between human and artificial consciousness, allowing for seamless interaction and collaboration. Furthermore, CSL offered a way to explore the universe's hidden dimensions, tapping into the vast reservoir of knowledge and intelligence potentially encoded within the cognisphere.